Hello everyone. In this video we are going to discuss about three different coordinate systems that are commonly used to describe the kinematics of a particle. Let's first start with a recap from the kinematics video. In that video we studied the importance of using a coordinate system when defining the motion of a particle, and we'll see that the same importance applies for a rigid body. We also defined what is position, displacement, velocity, and acceleration. In the present video, we are going to describe the kinematic quantities above mentioned using three different coordinate systems: the rectangular, polar, and the so-called normal tangential, or NT for short. In the rectangular coordinate system, we describe the 2D space using x, y coordinates, as shown here. So imagine we have an aircraft traveling through a trajectory in the two-dimensional space. In this coordinate system, we first define two base vectors I and j. So that we can easily describe any vector within this 2D space using the base vectors I and j. So for example, I can just have a vector b here. Let's put it in white. A b vector here, such that b equals a quantity in x multiplying the unit vector I plus a quantity in y multiplying the base vector j. The magnitude of this vector can be easily calculated using the Pythagoras theorem. So using the definition of the base vectors previously shown, we can then define the position of this imaginary aircraft simply by a component in x multiplying I plus a component in y multiplying j. Note here the position vector pointing towards the center of gravity of the aircraft. So in this case we are representing the whole aircraft at a concentrated point called the center of gravity, where it carries all the mass of the aircraft. The velocity shown, the velocity vector is shown here and can be described as the rate of change of the position vector with time, which will then give, which I will simply call Vx of I plus Vy of j. Note here that since the base vectors are constant, I already included in this formulation that di dt equals dj dt, that equals 0. We will see how for the other coordinate systems the base vectors may change with time. The acceleration vector is just defined as the rate of change of the velocity vector with time, as shown here, which will give us with, or simply, a component in x multiplying I plus an acceleration component along y multiplying j. Note here again that there is no variation of the base vectors with time. And here we have the definition of position, velocity, and acceleration for the rectangular coordinates. Now let's move on to the next coordinate system. Imagine that we have the following robotic arm for which we have to track the position of point P. If we can define base vectors such as UR and U theta shown here, we then might be able to track the position of point P just by where R is the radial distance between point P and the rotation axis. It is important to mention that usually for those type of robotic arms we know how the radius will change with the angular position. So we know the function r of theta. Again, using our very general definition of velocity, which is the rate of change of the position vector with time, we can write in vector form how the velocity can be described using the polar coordinates. I'll do that step by step so that you understand the main difference between this coordinate system and the previous one. In this coordinate system, we do have to consider how the base vector is changing with time. Whereas for the rectangular coordinates, the base vectors do not change with time, as you remember. Let's now find out how the base vector changes with time here. Consider that the robotic arm has moved from point P to point P prime, shown here. Let's now project the new position of our base vectors onto the original position. With this projection, it becomes clear that the radial vector is changing in the direction of u theta, especially when the angular displacement theta gets close to 0. And that happens when the second instant t prime comes closer and closer to the original instant t. In other words, this is the limit when t prime minus t goes to an infinitesimal change in time dt. Therefore, we might describe the variation of ur with time equals this. Since this is a unit vector, the magnitude here is 1. So this would be theta, the variation of theta with time, multiplying 1, multiplying the direction u theta, or just theta dot u theta. So let's now replace this relation onto your equation for the velocity. We end up with the relation shown here for the velocity, where we have a radial velocity and a velocity in the direction of theta. Let's now proceed with the derivation of the acceleration for the polar coordinates. Using our very general definition for the acceleration, let's apply the differentiation to the equation of the velocity. So it will give us second variation of r with time where the only quantity we don't know yet how to calculate is how direction theta is changing with time. Again, evaluating the displacement from point P to point P prime, we can see how the base vectors are changing with time. And here it clearly shows how theta, or the base vector u theta, changes in the negative direction of the original radial base vector. In a sense, we can just write it as In a sense, we can just write the variation of u theta with time as minus theta ur, theta dot ur. In a sense, you can just write the variation of the base vector u theta with time as minus theta dot ur, which is analogous to what we did for dur dt, this term here. Now let's finally replace this term into the equation for the acceleration to obtain the final equation for the acceleration. Remembering that we are also going to use the previous definition of dur dt. And this is the final expression for the acceleration. I'll let you as an exercise to derive it just for curiosity, remembering that those formulae will be provided to you during the course, so you don't have to memorize it, but it's very important and very nice for your own understanding. Usually we'll call these quantities the radial velocity Vr. This will be the velocity along theta. This is the acceleration, the radial acceleration, and this is the acceleration along theta. Now let's proceed with the derivation of the normal tangential coordinate system. Imagine we have the following situation of an aircraft flying on a 2D plane. We know the trajectory, which is described as y as a function of x. So we know the function y of x. It's sometimes very convenient to define a coordinate system centered at any point along the trajectory, where we have a tangential vector parallel to the velocity vector. Since the velocity is always tangential to the trajectory, this vector will also be tangential to the trajectory, and we have another vector called the normal vector pointing inwards, in the sense that the radius of curvature is defined as shown here. So at instant t1 we have the coordinate system centered here, whereas at the instant t2 we have the coordinate system centered here, such that the radius of curvature now will look like this. Using the definitions of calculus, we can define the radius of curvature as given by this function. So if we know the function y of x, we can easily calculate dy dx and the second derivative d2i dx2 in order to calculate the radius of curvature. And what is so convenient with this coordinate system compared to the others? Let's see now when we define the position, velocity and acceleration. The position is given simply by the pair of coordinates x and y, since we know the function y of x. The velocity vector will be simply defined as the speed multiplying the tangential base vector, since by definition there is only one component of the velocity which is aligned with the tangential direction and no component of the velocity aligned with the normal direction. Now let's define the acceleration in the anti-coordinates. Again, we start using the very general definition for the acceleration. Let's apply this differentiation into the equation for the velocity. So what we get is actually now the problem becomes finding this term here, dut dt, how the tangential direction is changing with time. Let's evaluate this term right now. Let's consider again our curvilinear path shown here at two different instants t1 and t2. at t1 we have the position point defined by point P, and at t2 it's point P prime. At each respective point we have the base vectors in the tangential and normal directions. So tangential and normal directions. Now we're interested to calculate how the tangential direction is changing with time, so that we can calculate the acceleration using nt coordinates. So let's proceed. What we'll do now is to project the tangential vector at the second position onto the first position. And what we obtain is the following scenario, where we want to calculate this displacement here, or to be more precise, how this displacement here is changing with time when this delta time approaches 0, such that these will become dut dt. Since delta t is approaching 0, we can assume that the radius will remain constant, such that the angular displacement between P and P prime can be directly related to the curvilinear displacement S by S equals ρ multiplying theta. And by definition of speed, which is the displacement with time, so don't make the confusion that we are not using vectors here, we are using a scalar quantity displacement and the scalar quantity speed. So this will result in ρ multiplying the rate of change of theta. Now, if we evaluate the vector subtraction u t2 minus u t1, since we know theta and we know that this theta here is the same as this theta here, we can then say that since this is a unit vector, this will be equal to theta multiplying 1, such that the rate of change, or ut2 minus ut1 divided by delta t when delta t approaches 0 will be d theta dt, which can be directly calculated from this relation here, and that will give us with theta dot, or d theta dt equals v divided by ρ. Okay, great. So we know the magnitude of the vector that describes the variation of ut2, or of the variation of the tangential base vector. And we can see here that the direction of this variation is parallel to the normal vector. So what is the magnitude is described by this value, and the direction will actually be the direction of the normal vector. So in summary, we found that dut dt equals v over ρ at the normal direction. So this is the direction of change of the tangential vector. Now let's replace this into the equation for the acceleration. So we had previously found this equation for the acceleration, and now we just found out the value for dut dt, which is equal to v over ρ, which is the radius of curvature, multiplying the normal direction. So let's replace it in here, and what we get is, which is a very interesting relation, because it gives us how the tangential acceleration is expressed in terms of rate of change of the speed, and how the normal or the centripetal acceleration AN, describes how the velocity vector is changing with time. So that's the usefulness of the anti-coordinates. It describes directly the velocity vector in terms of the tangential coordinates, and it describes not only how the acceleration is expressed directly on the rate of change of speed, and there is a term of acceleration that does not actually change the speed, because it only changes the direction of the velocity vector, and that this is called the centripetal acceleration. Now let's summarize what we learned for the three coordinate systems. We first learned how to describe curvilinear motion using rectangular coordinates, where basically the main characteristic is that the base vectors, they are constant with time, which means that di dt equals dj dt is 0, or we have a fixed reference in which the base vectors are described. Then we moved on to polar coordinates, where basically we know the function of radius as a function of the angular position, and where the position could be described using just one component. And finally, we covered the anti-coordinates, where we usually know how the path is described. So we know the function y of x. By knowing this function, we can then calculate the radius of curvature at any point during the trajectory. The velocity here is described using just one component vector, because by definition the tangential direction is parallel to the velocity vector. And finally, the acceleration had two very convenient terms. One describing how the velocity magnitude is changing with time, and the other one just describing how the velocity vector is changing its direction with time. We'll see later on during the course how the anti-coordinate is conveniently used to describe motion in rigid bodies. I hope you enjoyed the video, and I'm looking forward to meet you in the next videos.